Good evening and welcome to the last Newcomen Society lecture in London of this year, halfway through the 2025-26 session, of course. And tonight we are going to be regaled by Dr. Fred Starr. Fred, we've all known, but we don't know enough about him, so I'll read this. Fred graduated as a metallurgist, which is interesting given the title, but Fred is a good science and engineering historian, researcher, and generally knowledgeable person. Fred graduated in 1966 from Battersea College, now University of Surrey. He joined British Gas London Research Station in Fulham, and he was there for 30 years, moving from failure investigation to leading the company's research on high temperature materials. Did a lot of work with the European Commission on energy conversion, including Stirling engines and gas turbines and steam plants. There must be a good lecture in steam in your knowledge of Stirling engines somewhere in there, sir.
Absolutely. Unfortunately.
So he's made something of a switch with the Newcomen Society to an interest which he's published a lot on aircraft engines and so forth. And now he's going to talk to us tonight on the Wright Brothers at the last laugh, the return to unstable flying machines. Over to you, Fred.
Thank you very much. Well, this is really, thank you all for coming, by the way, on an evening like this, so close to Christmas when you could be swilling it way on the, nice places. This really, in a sense, is a two-pronged lecture. I'm obviously talking about the Wright brothers, but I'm also talking about what these two people did. Professor Padfield at the University of Liverpool and Professor Kulik at the California Institute of Technology, because what they did is now 25 years old or so. When the centenary of the Wright's first flight was coming up, intelligent people who'd got an interest in aeronautics decided to ask the question, well, how good were the Wright flying machines? We know that they flew in 1903. We knew that over the next couple of years or so, they got better. And then there was a long switch off of around about 4 years in which the world heard nothing about the Wright brothers. Well, we'll see maybe why that was the case. Right, can we switch? Right, well, here is this very well-known picture, which I think tomorrow will be 122 years since this picture was taken. It's colorized, of course. I've always thought a problem with this picture is that you can't really see what the airplane looks like. But here we have Orville in the first flight and his brother who's been holding onto the wingtips. And it was just a very short hop. Later that day, they reached something like about 300 yards or so and decided to stop doing anything and go and have lunch. I think that was a good idea, actually. Over lunch, it was so windy there, a gust of wind caught the plane, picked it up in the air, and smashed it to pieces. The Wright brothers then took the plane home and never did anything with it. The next time that they flew was a year later, back in their hometown. And there's something I'd like to emphasize about the Wright brothers. People talk about them as bicycle mechanics. That's what they were called in those days. Well, here were a set of bicycle mechanics who could afford to take their pieces of aircraft 600 miles from where they lived to what they saw as the best place to test aeroplanes, out on the east coast of America. This is equivalent to you or I doing experiments up in Aberdeen. Where would we get the money for that from? It shows that the Wrights were successful businessmen. Okay. Well, here is a better picture of the Wright aircraft. And we see Orville lying down, manipulating the controls, and particularly the position of this tail here. All the Wright aircraft were tail first, and this gave them very good flying properties, but it made them, particularly in the way that they had the center of gravity of the aircraft, difficult to control. Okay. Well, I had to resent this comment about me taking up an interest in aircraft latterly. I've always been interested in aircraft, always. I didn't join the aircraft industry because I didn't think I'd got the mathematical ability to be there. But you see the kind of thing I was doing. This is round about 2004 when I wrote to the London Review of Books about a book which had just come out about the Wright brothers. Can you click? It's quite a long piece here, but what I said was the Wrights designed their aircraft to be unstable, knowing that with good controls like wing warping and rudders, they would be as easy to fly as the bicycles that they had made. This was perhaps an overstatement. They didn't really understand about stability. What they did understand is that if you had good controls, you would have a safe aircraft. Like if you've got a bicycle with good steering and you've taught yourself to cycle, you've got something that you can fly, you can ride, and if it's an airplane, you can fly. Okay. Well, of course, in America, they made something of a thing of the fact that with the 100 years since the first flight, there was going to be a sort of exhibition at the place in Kitty Hawk in North Carolina, where the flights, the Wrights originally flew. Well, I could have gone there. I'd got the time and I'd got the money. One of our members, Ed Marshall, did actually go out to see all of this. And I thought, I don't want to go because I knew enough about the Wright flyer that I thought it probably wouldn't get into the air. And if it did, it was so unstable, we might end up with a horrendous crash, and I didn't want to have anything to do with it. Okay. Well, this is about as far as they got. They got a little hop off the ground, and that was it. That was the Wright brothers flying replica. Okay. Well, here are the Wright brothers. The French said just a pair of bicycle mechanics, and here is their shop here. I think Roy has been to see this. Yeah, in Daybourne. The whole assembly was taken off to Ford Museum in Daybourne. Okay. Well, you see, it's quite big. They're not making bicycles by mass production, but they're making them at quite a high price. In today's money, I think you're talking about each bicycle was going for about the price of a small car. They were making money. They were earning $3,000 a year, which I think in real spending terms would probably be $500,000 or so. Okay. There are the two of them, Orville and Wilbur. Wilbur, who was the cleverer one, unfortunately got typhoid in 1912 and died. His brother continued on, almost riding on the fame, although he was honoured, of course, in the aeronautic community. Okay. Well, they made their bicycles by hand. They were skilled mechanics. They were successful businessmen. They'd run two businesses, including the bicycle business. And when they got into aircraft, they did that partly because the bicycles were starting to be made by mass production, and they were looking for something else and thought, well, here is this airplane thing. We're interested in aircraft. Why don't we try that? So they were designers. Okay. Research engineers. They did a proper research job. And you could spend a morning talking about what the Wrights had done in terms of aeronautical research, producing wing sections and getting lift-to-drag ratios and so forth, and criticizing what other people had done before their time. Okay? And they were the first professional test pilots. Certainly in America, they before they actually flew the Wright Flyer, they were testing gliders. They'd got to know how to handle aircraft. They knew what happens when an airplane goes wrong. Okay. And this is the sort of thing that they were doing as engineers and designers. Their aircraft, unlike many of the aircraft that had been built before their time, were structurally designed, sound. They were based on the Pratt truss idea that you've got with bridges. They'd got aerofoils, which they'd produced in their own wind tunnel. They developed the idea of actually controlling an aircraft in all three dimensions. That's turning, going up and down, and rolling. Nobody else had thought about this in those kind of terms. They thought about aircraft stability, and they sacrificed aircraft stability to maximize lift. And it's one reason why their aircraft were able to fly. Before they knew they needed an engine, and they knew exactly how much power they needed to fly. They weren't guessing. And particularly important, they produced the first genuine aircraft propellers that anybody had ever made, because they designed their propellers on the basis of wing design. A propeller is a kind of wing which has got to hit the air at the right angle. And they couldn't get a good engine from anyone, so they designed their own engine. I think that's pretty good, isn't it, from so-called bicycle mechanics. Okay. Here is the Wright's homegrown aircraft engine. Not particularly powerful. As I said, I didn't think if they tried to do it, if they tried to replicate what the Wrights had done in 1903, they wouldn't do it because the aircraft didn't have the right, just enough power. It's aluminium aircraft engine, the first one of its kind, built by the Wright shop mechanic, but designed by the Wrights. Okay. And then we have the propellers. Well, if you look at propellers that people were coming up, really before that era, and also when the French and other people were trying to fly, and you look at the crudity of their propellers, you see that people just didn't have a right idea. They were thinking in terms of ships' propellers. Well, the Wrights, when they started to look into the subject, they found that there was no science to ships' propellers at that time. Ships' propellers work in water. They rotate quite slowly. They're working in a high-density fluid. Aircraft propellers are quite different. Okay. And here we have a genuine Wright Brothers aircraft propeller. It's basically a wing in which it's been twisted the right point at various diameters, so it's hitting the air right. The angle of pitch, therefore, varies with the diameter. It's made of high-strength wood, laminated spruce for strength and lightness, high speed of rotation, and it's designed for air, not water. Okay. Well, we go back. This is the original picture, not colorized. Okay. They were very lucky. The wind speed at round about 27 miles an hour that day was just right. It's not realized by people who haven't gone into aircraft design that there is a particular speed by which when the aircraft fly, that the drag is a minimum. If you go below that speed, the drag gets higher. And I think most people know that when you go higher than that speed, the drag gets high. Because the wind was just right, you might argue that the Wright aircraft were wafted into the air. It was also ideal for maximum propeller thrust because they designed the propellers for about 27 to 30 miles an hour. The air was cold, the air density was high, so that is giving you more thrust from the propeller. And because the air was cold, the engine was performing very, very well. Okay. The Wright flyer was very unstable. It was only the fact that they were skilled already at piloting aircraft that a crash was avoided. This is a little table of what the aircraft regulation people ask for in terms of aircraft. Well, you obviously have got, you want your aircraft to be one where the pilot skills are not a factor. So the next 7 or something like that, and the pilot dies, you stand up and say, I'm an engineer, I can do anything, I will land this plane. Well, the reason why you're able to do that is because commercial transports are in that category. Pilot skills are not a factor in flying this aeroplane. Well, you go down this table, and I would guess that if you're a fighter pilot, you're in a different situation completely. You need a good pilot, and you go right down the list, whereby you have to be a test pilot to actually get the plane into the air and then back on ground in one piece. Okay? This has been said about the Wright flyer, The Wrights were not only the first to fly, but managed to fly one of the most difficult to control aircraft in the past 100 years. And that's coming from the people who were doing the work back about 20 years ago, looking into the Wright aircraft. They were extremely difficult to fly. Okay. Well, the focus in this talk is really about the planes going up and down in the air, up and down. But the Wright brothers found that they had to be able to turn aircraft. And they mimicked the birds essentially by making the wings bend in the way that birds do. So, okay. What the Wrights were doing with their wings was bending the wings like this bird is doing. You see, it's turning into the screen, as it were, and therefore it's got less lift on that wing and more lift on the other wing. That's an entirely different subject, but I'm just saying that is what the Wrights were doing to enable them to fly properly. Okay? Well, I started off by saying, well, the unusual thing about the Wright aircraft is that they had the tail first. Okay? Why did they do that? Well, they could actually see what the tail was doing. And if I could make a point about modern aircraft, some of the crashes which have occurred have happened because the pilots simply cannot see what's happening to the ailerons and to the rudder and to the elevators. They're completely relying on what's going on in the cockpit. The Wrights could see what was going on. Okay. A great advantage is that both the wing and the forward tail are providing lift. The tail in modern aircraft is actually reducing lift. It's forcing the aeroplane down. It's one reason why we're starting to switch to planes with the tail, this kind of forward tail, a canard. Okay. Pilot given crash protection. Okay. And the aircraft is very maneuverable. Okay. Oh, and a mushy stall behavior. The way that they got this, and also the center of gravity, is that if the aircraft ran out of lift, instead of just going down in a nosedive, it just flopped onto the ground in a fairly easy manner. Okay. But this means that the aircraft is, in aeronautical terms, statically unstable. It needs an experienced pilot and it needs really good controls. Okay. By statically unstable, I think everyone here knows what the center of gravity is. It's the point whereby you could suspend the aircraft from a string and it would be absolutely level. The neutral point is an aeronautical term which is used to try and show how stable the aircraft is. It's not quite where all the lift forces act, but it's a useful aeronautical term. Let me go no further than that. And the distance between those 2 points is called a static margin. It's always got to be positive, but the Wrights had got a negative static margin of about -20%. totally unstable. Okay. This is what happened. Okay, click. Either wanted to climb or click, wanted to dive. It needed an experienced pilot to control its behavior. Okay. Well, what these people were doing 20 years back was saying, well, what would have happened if we'd been flying the Wright Flyer? And this is the kind of motion. It's up and down because the aircraft, the model aircraft is in a wind tunnel. They're feeling the forces on it. They know whether the forces are causing the airplane to go up or down. And this is the result. The airplane is just not flying straight and level. It's continually going up and down until I think at this point, the chap who's running the wind tunnel gets too tired of trying to do it, and he just gives up. And effectively, the aircraft starts to crash. Okay. So once again, the Wrights were not only the first to fly, but needed to fly one of the most difficult aircraft to fly in the last 100 years. This is the kind of thing that was going on in these tests. They were having to manipulate the controls so much. You're talking about 25 control movements in 5 seconds. Now, think about driving a car. Are you having to do that as much as that? You're talking about maybe at the most one movement, even in difficult circumstances, probably about once every half a second. This is getting beyond human tolerance. Okay. Well, the 1903 model was very unstable. They did some more work in 1904. And then in 1905, they sat back and they did not quite a completely redesign, but they knew that they needed more wing area. They needed a more powerful engine. And in particular, they had to make the aircraft more stable. But the way that they did that is that they moved the center of gravity of the whole aircraft forward, and they put on a bigger canard to control the up and down motion, and a bigger rotor to help control left and right movements. Okay. And this is what they came up with. From hops of 250 yards or so in 1903. Here is flying from a field which is not very far from, which was on the outskirts of Dayton, flying 24 miles in 39 minutes. They only stopped because the engine ran out of fuel. Okay. Well, they got a lot of adulation, but the French in particular said, well, they're very good, but you really need to be a very good pilot to be flying the right aircraft. We think it's better to have tails on the aircraft. They're much more easy to control. This static margin, which nobody knew about for the next 20 years or so, becomes positive. And that's how airplanes have been, what they've been like ever since, with a tail at the back until quite recently. Okay. So we have with the Boeing 737, and some of you will have heard about the crashes on this, but here the static margin is 16% or so. You've got the lift force up, round about the middle of the wings, and the center of gravity further forward. Everything works well, except you've got a downward force on the tail of about 5,000 pounds. Well, that's got to be paid for. That's equivalent to another 20 passengers or so, or maybe another 500 miles of range from the aircraft. The tail looks good, but it's a parasitic part of the aeroplane. Okay. Well, people have looked at Canard aircraft back in the 1940s. It was quite clear that the piston engine aircraft was reaching the end of the line, and people were looking for better ways of designing them. And one way was to go for this Canard type. And we have the XP55 Ascender. It was fast, but 3 out of 4 prototypes crashed. Because if you really want to try and make a Canard aircraft stable, you've got to put the center of gravity quite a bit forward. It means that the Canard is producing a lot of lift. If it stalls, that's it. You can't do anything about it. It's worse than an aeroplane with a tail. Okay. But they've come in various odd ways. We have where you're looking for very good range and you haven't got a lot of power. The first cross-channel flight, man-powered flight, was the Gossamer Albatross, and you've got the Canard up front. That's maximizing the lift of the aircraft. The tail, the ordinary tail, is wasting energy. And if you're pedaling an airplane, you haven't got very much energy to spare. Okay. And then we have the round the world aircraft. Again, they went for a Canard design. In both of these aircraft, the pilot had to work really hard to keep the airplane flying, because a Canard, if you take the full advantage of it, is not a very stable situation. Okay. The only real attempt in commercial aircraft is the Beechcraft Starship. It didn't do very well. Okay. The Canard had to move forward when landing because the flaps were coming down, and the flaps which were not very good at reducing the landing speed, were tending to make the aircraft nosedive, and they compensated for it by making the Canard move forward. So it, not a V, became more straight. Okay. But what started to happen in fighter aircraft now is that we've got Canards coming in, and instead of calling it unstable aircraft, they say it's relaxed stability. Well, it's like somebody who has got an adulterous affair, and he says, I've got a relaxed marriage. Okay, right. This was the first attempt at doing this. This is a Swedish aircraft. It needed sophisticated instrumentation, servo mechanisms, computers, fantastic software design, because what is going on is that the aircraft is supposed to go the way that the pilot is moving the controls. Okay. So just to make sure that the electrics work properly, we've got 4 pieces of wiring going to each system in the aircraft. Okay. The first 2 prototypes crashed. And that was put down to bad software design. Sorry, Dan. Okay. The French have gone this way. This is their Raphael. The static margin in this is minus 15%. Remember that the Wrights were at minus 20%, and the Boeing 737 was at plus 16. Okay. And then we have our own aircraft, the Eurofighter Typhoon. That appears to have a static margin of about 20%, but the manufacturers will not release the figures. Okay. But I mentioned earlier that one of the problems with that XP-55 in the 1940s is that once the Canard lost lift, you were in real problems. Well, I think this is why on the Eurofighter, you've got the Canard able to move over such a wide range of incidences so that if the aircraft starts to stall, you can get the Canard flying again and at least try to recover. Okay. The weak point in all of these systems is probably not so much the software, it's the instrumentation. You need good instrumentation. And again, talking a bit about history, this is a Northrop aircraft built in the 1940s. Looks absolutely terrific. It was so terrific, it was used in the War of the Worlds 1950s film. But because it was so unstable, it didn't have a tail. It never flew straight enough to be an accurate bomb aimer, accurate at bombing. Okay. Well, the Northrop company came back, I should think 50 years later, with their B-2 bomber, which is also tailless. This is really designed not so much for high-speed flight, but radar invisibility. It crashed because the sensors on the aircraft got wet and stopped working. The computer couldn't deal with that. It took the airplane into the air and caused it to stall and crashed. And there was $2 billion. I think even President Trump would want to know about that. Okay. Well, we're getting quite near the end here. And a feature, I don't want to worry any of you, but modern commercial transports are getting closer and closer to the instability. And they're doing it in various ways. But the Boeing 737 is a classic example of doing this by subterfuge. You'll notice how big the engines are on this and how close they are to the ground. Okay. Well, what happened? This is one of the crashes, the flight pattern for one of the crashes. Here is the blue line is the altitude of the aircraft taking off, takes off at sea level, reaches about 2,000 feet, and then suddenly goes into a bit of a dive. And then it starts climbing again and is obviously not in control. The people are not in control because it's going up and down and up and down and up and down. you cast your mind back to that picture I showed you of the Wright brothers aircraft and how that was going up and down. And the pilots just simply gave up and the aircraft crashed. The reason why this happened is that they had in the aircraft what is called an angle of attack indicator, which told the computers, not the pilots, exactly how the aeroplane was flying. Was it flying near the stall, or was it in a dive, or whatever? The thing is that the way that the system had been arranged is that the pilots had got no indication of what was going on. They were moving the control column. There was no feedback through the control column at all. It's like you suddenly getting into your car and you're driving along the motorway and then you try to turn off and you find that, well, the steering wheel is not connected to the front wheels. And they couldn't see what was going on. That's the difference between the Wright brothers and modern aircraft. They couldn't, modern pilots can't see what's going on. Okay, right, now how do we do this? I want you to click on this and try to bring it down. Well, this is, if we don't get around to seeing it, this is a Wright Brothers replica, actually an attempt at a flight, and it does fly. And you'll see, hopefully, I hope we're not going to have to wait 3 minutes. Now, Huffman Prairie is the place where the Wright brothers did their first successful flight. As I mentioned earlier, I think it was 24 minutes, 24 miles in 39 minutes. And here we are, they're starting off. Can everyone see it? Well, you've got the two propellers. I mean, that was quite clever. By doing that, you avoid kind of asymmetric effects, which you get with one propeller. Unfortunately, we don't seem to have the sound. But let's just have a look at the picture. They have a kind of catapult device to help get the aeroplane into the air. It's jumped. Ah, here we are. You see, you can't keep it level. It's going up and down. And now he's turning it, or trying to turn it. And I think he was hoping to get back to the starting point. And it ends up. Pilot's okay, climbs out. Waves. And any landing you can walk away from is good landing. Okay, well, yeah, that's very funny. Isn't that funny? The same pilot took the plane up during the afternoon and crashed it and broke his back. That's one reason I didn't go on that in 2003, because in my bones, I knew that something like that would happen. Well, that's it, gentlemen, ladies. Okay. So if you would like to watch winter lambing. Okay, well, the last slide was, thank you very much for coming. I hope you've got something out of this. And are there any questions?
Thank you very much, Fred. That was interesting. Yeah.
Right, you say that these bicycle repair people suddenly thought, oh, we're getting to flying. Well, where did the, middle Ohio, a long way in sort of the middle of America, where did they get the inspiration? Who were they finding out
Well,
about flying?
the story is that their father brought home a toy helicopter. This must have been when they were about 10 or 11. And they kept up kind of a general interest. I think the idea of flying was probably in the air as much as it was going to the moon.
But when did they start gliding?
This was around about 1901.
Yeah, because that was quite late, because there was a lot of gliding going on before then.
Yes, well, if you look in the New Common Archive, there's a paper in 1903 on George Cayley's diaries, and Orville Wright wrote in reply, having got a preprint of the paper, saying that he felt that Cayley understood aerodynamics better than anyone until Lilienthal at the end of the 19th century. So there was a lot, I mean, they weren't just bicycle mechanics. These were guys who knew about what was going on.
Oh, that's
from that sort of correspondence with the society. I think that shows that they were pretty clued up about what they were trying to do.
That's absolutely right. And talking about, do you want me to, which microphone do you want me to use? Yeah, talking about Cayley, who was around about 1830, 1840, and did a lot of experimentation, and actually built a glider in which he stuck his coachman, and he flew across a valley in Yorkshire. And the coachman said, "I wasn't employed to be a pilot. I was employed to be a coachman." But the thing about Cayley is that he flew small gliders and big gliders, and he recognized what was needed to make an aircraft stable. And we see that in modern aircraft. If you look at modern aircraft, you'll see that they have a shallow V when you look at the front. That enables them to that they don't turn to go into a steep roll. They're quite stable. The other thing which he recognized is that there was a kind of a back to front dihedral in the aircraft, that the angle of incidence of the wing had to be positive, and the angle of incidence of the tail had to be negative. And if you then have got the center of gravity in the right place, a glider will fly properly. I certainly remember when I was a kid and I was flying balsa wood gliders, they provided a lead weight in the nose, and the lead weight would invariably get lost and the airplane wouldn't fly after that. Well, he recognized that you needed that stability. Well, if you have too much stability, you can't turn an aeroplane. And the Wright brothers, because of their background with bicycles, realized that if you've got good controls, stability is not so important. But they did change. If you look at carefully at the 1905, the cross section of the 1905 glider and the 1903 glider, the wings of the 1903 glider are actually a V upside down, which made it very unstable when turning. The 1905 glider has got a very, very slight V, the right way, as you might say. And also the way that they put the canard made the aircraft more stable. Cayley was a real genius. All that he needed was a petrol engine, which of course didn't exist at the time.
Thank you, Fred. That was absolutely fascinating. I got a comment and then a couple of questions. I commented I had a student a few years ago who wrote his PhD thesis on the 8th Duke Argyll, who was quite a significant figure in British aeronautics in the sort of mid 19th century. He wasn't the Secretary of State for India and jobs like that. Now, my first question is, why are those little wings called canards? It's in my observation, canards are either ducks or Tolstoy put around for nefarious purposes. And my second question is, you referred very, very briefly near the beginning to the Wright brothers having wind tunnel, and I wonder if you could say a bit more about that.
Well, in terms of the canard, nobody really knows where that story came from. It seems to have emerged when the Wrights took their aircraft to France, and there was quite a run up to this, that they built a shed to put the aircraft together, and the French are standing around waiting to laugh at the aircraft. Well, all I could say is that the laugh was on the other side of their face when the Wrights flew, but they had to make a joke about something. So they said, "Oh, it's a bit like a duck flying forward." That's all. Now, what was the other question about the wind tunnel? Yeah, well, they had a small wind tunnel which they actually ran off the petrol engine. They built at least 2 petrol engines, one for the aircraft, and they actually got a petrol engine for doing jobs around the factory, their little factory. And the wind tunnel, which I think was only about 10 foot in diameter, that was all that they were needed. Not a very good wind tunnel by today's standards, of course. No. There was a chap called Wenham in Britain who developed the wind tunnel. And because of that, he recognized that most of the lift from a wing comes from the forward portion. He presumably, I don't know this, but he presumably must have had manometer tubes linking into the surfaces, so he could see how the pressure was varying.
John Penn of Greenwich, the engineer, had built a wind tunnel in the 1860s. And
oh, yes, of course.
Very little is known other than it existing. But turning to Greenfield Village, which is where the The point about Henry Ford collecting for Greenfield villages, don't believe what you actually see today. You can't say that their building was as big as it was, because all he collected usually was the front and maybe the side if there was late information on it, and then told his men to get on and build something behind it that they could use. And in fact, the wind tunnel's still very much in the building.
Oh, you've seen it?
Oh, yeah, reasonably.
Oh, could you say something about it?
Well, no, not really. No, briefly.
Yeah, can Roy say
I
anything?
could have, if I'd known, I could have got my photographs out of it, which I've got at home as slides. But if you want to find more about that building, I think you need to consult the archives, the Ford,
Yeah.
Henry Ford archives,
Well,
which are there in substantial detail. But Ford took the bits that looked nice and then built behind them to
Yeah,
make it
yeah,
really
yeah.
big enough the way he wanted. It's actually in Greenfield Village.
It's one of the things I think it was they worked on the aerofoil shapes, didn't they?
yes, they did. Yeah, they were relying. They relied on what they'd learnt from Lilento,
Yeah.
the German, but they initially they didn't believe everything he'd said, and then they realized that it was actually a misinterpretation of what Smeaton had said about airflow and airflow forces.
One of the things you've talked about a bit is when you end up with control forces. So a more stable aircraft requires bigger control forces to point it where you want to go. And of course, all that comes with drag. So what the interesting thing to me is when you start getting away from those draggy things called tails and tail surfaces. I remember having a lecture once from Dr. Wallace
Hmm?
when I was a young graduate about how the tornado was all wrong because it had a tail.
Yeah,
And he was trying to get us back to the swallow, which is well worth looking at, because if you look at where the swallow, the big swing wing thing that Wallace flew.
well, I suspect that the Swallow, if it had flown, would have had the same kind of problems as the XB-49. I think that is you can't defeat the laws of aerodynamics.
Swallow. Yeah, I know nothing about Barnes Wallace designed a tailless dart, really, almost, wasn't it? Big
Yeah,
swing
yeah.
wing aircraft. That was aimed at being supersonic-ish plus. And that would have flown the models were flown in the late 40s, I guess. Maybe
No, the
50s,
middle
50s, maybe.
50s, middle 50s.
And this was going to be the thing that you could fly to Australia in no problem. I was a graduate at Weybridge in the early 70s. And Dr. Wallace was still there. And believed that this was the thing we should have used as a basis for the swing wing, what was then called MRCA, became Panavia Tornado, in that you didn't need a tail. And when you look at the size, particularly the fin and rudder on the Tornado, to get the turning forces that you need, you've got an awful lot of weight you're carrying around.
Well, I think the reason for that is that you've got the shift in the center of pressure when you go supersonic, so that you don't have the moment arm from the tail turning the aircraft, and that's an issue.
Yeah.
I mean, the tail is too big for a subsonic aircraft, but it's okay for supersonic. I mean, there's been a number of supersonic aircraft whereby they've had to increase the size of the vertical tail to keep it flying straight.
And is that a question of, you know, how much you use the rudder to steer the aircraft and how much you just use banking?
Yeah, yeah.
Because really, if you look at a modern airline of flying and you're staring down the wings as some of us idly do when we're flying
Wow.
somewhere, all you see is the high-speed ailerons moving.
Well, that's what I just would like to point out about the Wrights. So coming back to you, what you were saying about the absence of a tail. Birds don't really have tails. They don't really have tails.
They don't have vertical tails.
They don't have vertical tails. What they do when they go into a turn is, as you saw from that picture, the bird turns itself, and then using the elevators, as it were, in the tail, it goes round in a circle. But I've always felt that the thing about bird flight is like me standing here and walking across the ground. I do it without thinking. You see the efforts by robots to do the same. And it's laughable, at least at the moment.
Just one quick question. Burt Ratton's designs, Easy Fairy Ease and things like that. The Burt Ratton design,
Yeah.
I understood that the Canard was designed to stall, to stop you like losing control.
Well, that's the story which is put about, which is true to a degree, but it all depends on where the centre of gravity is. And that's why that XP-55 Defender wasn't very successful. They put the centre of gravity so far forward that the Canard was having to carry a lot of weight. And if that stalled, it would mean that you were in problem. Whereas if you have the centre of gravity right, just as I was saying about the Wright brothers, if the aircraft started to stall, the plane would just more or less flop onto the ground in a very nice, comfortable sort of way.
If anybody online is looking and wanting to ask questions, there will be a way through. Is it through chat?
Yes.
Raise a hand or something, we'll pick it up.
Is it
One thing
possible?
that did strike me, Fred, was if you built a Wright Flyer today and you put a modern electronic system on as an artificial stability, would it work? Because
Yes.
one of the things that struck me was your plot of the control movements was not dissimilar to the things we saw when we were trying to build man-powered aircraft in the early 70s, 60s to 70s. They did the same sort of thing. Now, part of that was because the guy who was controlling it was also aware about cycling to push a propeller along. But there was that sort of thing, and it was because of a very low wing loading, big wings, etc., lots of drag. As soon as you start banking the thing and losing control of it, you get your control movements in phase with the oscillations of the aircraft, and you get pilot-induced oscillation, blah, 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 and it crashes.
Well, there's no two ways about it. That's a very good point. And one of the other ways that they've had of simulating the Wright Flyer is to do it with sets of transistors and capacitors and inductors and so forth. And you can get the same kind of motion coming in. And effectively what you want is the right sort of feedback at the right time. But it also depends on having the right input from the air indicators, the angle of attack, and so forth.
Other than
Yeah, you've got a question?
Hugh, would you like to ask you? Thank you, Fred, for that excellent explanation. A couple of questions, really.
The remote to gallery.
I don't think we can hear people talking.
Sorry, can you hear me? Hello? Hello?
He looks pretty angry.
Hello? Can you hear me?
We can see you talking, but we can't hear you, so we're trying to rectify that, or we'll have to get something and
Well,
find a way of someone
I'm
repeating the question.
He needs to unmute himself.
sorry.
He's unmuted.
Yeah.
It wasn't then, he just flashed up mute.
please unmute yourself.
I am.
Unmuted.
He is now.
You can't hear me. Sorry.
The sound off today.
Sorry, the sound's off.
Have we got any luck?
Plugged in.
Don't think so.
No.
Sorry.
No.
Can't do it. Okay.
That's all the right notes and hold it up to the camera.
So there's quite a lot of people looking in.
Yeah, there's 55 people online, so 34 now. That includes probably Dan and Bill. But unfortunately, we couldn't hear Hugh's question.
Well, if Hugh sends me the
You
question,
send the question to Fred and we will get a detailed answer arranged.
right. No, I think your point about building a Wright flyer and having some electronics on it is a very interesting one. Yeah, yeah,
Because certainly, I spent some of my latter days in the aircraft industry designing auto stabilizers, designing the control walls for those, because all the airlines rely on your dampers,
yeah.
etc., to keep the aircraft effectively
Going straight.
going where you pointed it.
Yeah.
But they all come with a cost, because every time they move a rudder a little bit, the drag goes up. The drag costs money.
Yeah. Well,
So you then go to the extreme. If you look at the T-tail aircraft, the whole tailplane moves. So you use the elevators and then you trim the thing out so that you've got a nice aerofoil rather than aerofoil with a tab on the back, and that just reduces the fuel burn dramatically. So yeah.
I think we've reached the end.
Have we reached the end? Has anybody got anything else to ask Fred, or shall we just thank him very much for an interesting, thought-provoking evening?
Thank you very much for coming.
Thank you very much, Fred. I'm going to go and get rid of it and see what we've got on next. Because we will see you back here.
You switch the
year.
top down. You switch it off.
So assuming you're all back next year on the 14th of January, Wednesday, Lawrence Scales will be talking to us on the art of engineering. It's 6 o'clock here or online. You're most welcome. So thank you very much for the audience online, which is dropping back now. I think at the peak it was 55, if I'm told. So 50 odd online, a good number in the room. So thank you very much for it. Thank you very much for coming. Julia's going to say something about.
I really like dinner.
There'll be a dinner. Julia's arranged dinner, which is due down at the.
And there's dinner at the, I booked a table for 8, which is
Well, I've
at
got
the
some-
half yard. You said you were coming.
I'm going to get a free dinner out. But
Okay, so see Julia
my,
at dinner. Otherwise, thank you all for coming. See you next year. Meanwhile, have a peaceful and restful.
They're actually,
Christmas.
they're quite, sorry, they're quite effective. I mean, I learned the 8, this kind of was going on.